Hello everybody, welcome back. Just want to go through a couple of the basics just to deal with this coil and how to analyze this coil and remember some of the fundamentals, some of the concepts that exist with this electrical component. We get kind of focused in on some calculation and some numbers and we get really confident and comfortable with them, and we forget what is actually taking place and what do those numbers actually represent. So what I like to do with anytime I'm envisioning a coil, whether it be a transformer or an induction motor, this is a great way to start. And then I can think of what happens to the force. What are those forces that exist within that coil? What is torque doing? But it has to come from this fundamental and understand what those forces are. So what I like to do is I like to take this simple little diagram, and I can this is just a very, very basic coil, but I can isolate this from the primary of a transformer. I can isolate this from one of the stator windings within an induction motor and move it from there. So what I like to do is just to draw out an equivalent circuit. So an equivalent circuit just being, how could I analyze this? How could I lay this out as a circuit in order to understand what is happening moving forward? So this is an equivalent circuit, is simply a series RLC circuit. There's my series RLC circuit. So what this resistive component represents is the physical properties of this wire that I chose to make my coil. So that could be the physical properties of my stator winding. Could be the physical properties of my primary winding on my transformer. We use the acronym MALT, which is material, area, length, and the temperature. So that's what makes up the physical properties of resistance in this coil. So these contribute to resistance, which is R. Now the component down here, this is really what we're going to drive after with transformers and with induction motors. So this is my inductor. And that inductor is going to create two types of induction. And those often get mixed up. We have induction, inductive reactance, and inductor. Inductor is what we're talking about when we've made a coil. So this is the coil component, really the whole entire thing, but we kind of think of the inductor. When I have a coil, I have an inductor. So the two components that this is going to make up are my induction, and that is going to be self-induction and mutual. Induction. Might be a little bit difficult to read. Switch the pens up. So that's self-induction. So that is how a coil affects itself. So what we refer to this of a lot of the time is my inductive reactance. This is what self-induction, kind of in a simplified version, is. You can go much deeper to kind of really in depth with what self-induction actually is, and how all of the things are affected within it. But just as a fundamental, it's a great way to think of it. That is my inductive reactance. Inductive reactance is another opposition to the flow of current. Mutual induction, where mutual induction comes into play, is if this is my stator circuit, or the primary side of my transformer, the mutual induction happens to the secondary side. So if this is a rotor, we're going to have another resistive component, and an induction motor, squirrel cage induction motor, it's actually a short-circuited secondary. But this mutual induction is actually the voltage that's induced, which will turn into the E of the rotor, electromotive force, and I'm using E because this is now my driving force within that rotor. That's what the mutual induction actually takes place. So if I wanted to analyze this circuit, I could look and say, well, there is a voltage drop here. You're absolutely right, based on the resistance and all of these. So the voltage drop across there is going to be determined by the current that's flowing through it multiplied by the resistance. If I wanted to look at the heat that's dissipated, just based on that, I could do the I squared R of that winding. So if I have a voltage drop here, I will also have a voltage drop across this inductive component. So if I wanted to analyze what this is, well, now remember that's the induction component. So this voltage drop is going to be determined by the same current that's flowing through here times my XL. And that's also going to contribute to the voltage drop across that coil, which is going to turn into my electromotive force. So my voltage drop across that component, that inductive component, will turn into my driving force within that rotor. So that's why it's really important to understand where the self-induction is taking place and where that mutual induction is taking place. If this is a transformer, this would be the primary side, this would be my secondary side. It's the exact same principle. So it's really good to kind of take this back to its basics and remember what exactly we were trying to analyze within that series RLC circuit. Sometimes series RLC circuits can kind of seem a little abstract and maybe they're not that practical, but really understanding transformers and motors, this is a very, very need to know piece of information and where all of those properties actually come into. So that's going to be it for this video. Look forward to seeing you in the next one.